shift registers. Already we have seen this logic design which manipulates the bit position of binary data by shifting to the left or right. Logic design which manipulates the bit position of binary data by shifting left or right. Major application: serial data to parallel data converters. Example, design a 3-bit shift register with the following functions: S1, S0 function, 00 synchronous reset, that is SR reset, 01 that is S1 0, S01, then shift right. If when S1 have 1, S0 having 0, then shift left. When S1, S0, that is state 0, state 1, both are 1, then no shift. Partitioned design. Here, partition design. Here, this is present state. This max. This is set 1. Sorry, I have told that one set 1, set 0, set 1, not shift, not state. Okay. Present state here, next state, present state given feedback connection, and given to shift left, shift right. If shift left going, then like this. If shift right, here. Then here Y output. This is the register. This is the clock pulse. This is the reset for set. Clear? Sir, clear. No shift equations. No shift equations and a circuit. No shift equations and a circuit. PS0, PS1, PS2. All are input. NOT gate. Output. NS0, NS1, NS2. NS2, next state 2 equal to present state 2. Next state 1 equal to present state 1. Next state 0 equal to present state 0. That is NS2 here. This is NS2 here, PS2. Okay. Here NS1, PS1. That one here. Okay. PS0, NS0. Okay. PS0, NS0. Shift left equation and the circuit. Shift left equation. Here shift left, present state, next state. Here this is present state input. This is output. Here shift left, present state given connection, the next state. PS2 to shift left like this. So ns 0. Okay, then ps1 ns2 ps1. Okay, then ps0, this one given to and this. So this ps1, sorry, ps0 ns1. Okay, so shift left, understand. Now shift right. In this shift right, in the shift right, ps shift right, ps giving here ns next state present state. Okay, this is present state. Shift right, next state. Shift right, right, right. For example, ps2 coming to this not gate and we want to output to ns1, ns1 ps2. Okay, then ps1 given to output ns0, ps1 or ps1 given to ps1 given to ns1. Okay, then pso given to ns2, pso given to ns2. This is the shift to right. This one shifting to here, ps1 where ns0 output, ps0 output is ns2. Actually here in physical ns2 here. ns2 ps2 ns1 ps1 ns0 bs. This is the shift right. Then synchronous reset model. Synchronous reset model. Here synchronous reset this is all on ground. This is the output ns2 ns1 ns0. Synchronous reset model ns2 given to ground, ns1 given to ground, ns0 given to 0, ns2 0, this one, and ns1 and 0, ns0 here 0, ns0 0. Registers in registers, these all are the registers. Okay, this register NSA 0 to 2 vector input. Here PS 2 to 0, it is 0 to 2 output vector. Plug in here like this, and then here also. Okay, clock and the for reset button, clock and the that is preset. No. Here connection clock okay, clock here only clock here only, and then reset clear in clear NS2 given PS2, NS1 given to PS1, NS0, that is next state 0 equal to percent state 0. This is the output 0 to 2. This is total design. In this total design, yes, reset here. Yes, reset NS0 to 2 and shift right 0 to 2 PS to 0 to 2 NS0 to 2 PS first shift left, shift right, shift left buffer. So here in shift left underscore left PS 0 to 2 NS 0 to 2 vector buffer PS 0 to 2 NS 0 to 2. Okay, here S1 S0, here given 3 PDFF output clock. This is reset. This is 3-bit D flip flop. Here again we have to remember design a 3-bit shift registers with the following functions: S1 S0 function, both are 0, S1 set1 set0 set1 set0 are both are 0, then synchronous reset both are okay in function, and then in 0 1 shift right